everyone, and welcome back to the Jamaican Geologist YouTube channel. This is episode 13 in the Geology Foundation series, and today we will be discussing water resources. Just like the minerals we discussed earlier in this series, water is also a geological resource. The study of water within the context of geology falls within the realm of hydrogeology and hydrology. I spoke about these two subdisciplines of geology at length in a video I did on here for World Water Day 2025. But to simplify, hydrologists study surface water like rivers and streams, and hydrogeologists study groundwater in aquifers. Water is the most important resource to life on Earth, and I believe it is often taken for granted. When the average person turns on a faucet in their bathroom or kitchen, or they flush the toilet, they are not thinking about water in aquifers or rivers, or the geology that stores water in some place, or the engineering behind getting it to their home. Most people just know they use water in their home and they get a bill at the end of the month which they must pay. Those individuals who turn on the faucet in their home and get water are quite blessed though. According to most sources, approximately 1 in 4 people globally, or about 2.1 billion people, do not have access to safely managed drinking water, meaning water that is located on premises available when needed and free from contamination. So the uninitiated may ask, what does this have to do with geology? Well, stay tuned to find out. So, about 71% or so of the Earth's surface is covered by water. The other 29% is land, that is continents and islands. So, of the 71% that is water, the vast majority of that is salt water, the seas and the oceans. Of all the water on Earth, 97.5% is salt water and 2.5% is fresh water. And of course, fresh water is what we humans depend on for life. Fresh water is consumed and it's used to clean and in industrial processes, among many other things. Of the small amount of fresh water on Earth, most of it is trapped in glaciers or ice caps, about 68%. Surface water in rivers, lakes, and ponds makes up about 0.3%. Groundwater is about 30%, and the rest of the fresh water is atmospheric moisture or moisture in the soil. So it is abundantly clear that most of the water comes from groundwater sources, most of the fresh water. Most of us are familiar with the water cycle. We were introduced to it in our primary school science classes. The simplified version we were introduced to talks about evaporation, condensation, precipitation, and then surface water as runoff. And some might go on to talk about the percolation, that is water going into the soil. Some might even mention that there is groundwater stored. When teaching children, there is an acknowledgement that there is groundwater, but that's sort of where it ends. And a lot of the time, there's more to it than that. And I understand we are dealing with children, and it's important to keep concepts simple. But considering we get most of our water globally from groundwater sources, perhaps we need to talk about groundwater just a little bit more when we introduce the water cycle to children. That's just a thought. So, an aquifer is a layer of rock or sediment that can store and transmit water. Think of it as an underground sponge. Some rocks allow water to flow easily while others block it. Aquicludes completely block water. Aquitards allow only slow water movement. Understanding these differences is crucial for managing water resources. And two key properties control how water behaves underground. Porosity is the percentage of rock that is empty space and can hold water. Permeability is how easily water can flow through a rock, and this is facilitated by how connected the pore spaces are. Primary porosity comes from the space between grains, and these spaces formed when the rock itself was forming. Secondary porosity comes from cracks, fractures, and dissolution features that formed after the rock's formation. Remember in the episode on geological structures, I spoke about faults. Faults are a good facilitator of secondary porosity. And both primary and secondary porosity, as well as permeability, are essential for determining how aquifers function. So most aquifers occur in sedimentary rock units. The most common aquifers tend to occur in limestones and sandstones. And this is because sedimentary units contain high porosity and are also permeable. And they're permeable enough to transmit water. Sedimentary rocks have primary porosity, and secondary porosity is created as well, especially in limestone environments. Limestones have primary porosity to begin with. When limestone forms from shells or coral or carbonate mud, it often has pore spaces between the grains. Sometimes though, compaction and cementation during lithification can reduce this primary porosity, and limestone can dissolve over time, forming fractures, cavities, and caverns. This is a form of secondary porosity, and it allows water to flow more easily in certain paths. Igneous rocks can form aquifers too, but this is a lot less common than sedimentary units. This usually occurs from secondary porosity as the rocks are weathered or fractured enough to increase pore spaces and permeability. There is, however, a case to be made for primary porosity in igneous rocks. If a rock is vesicular enough, like some basalts, this creates primary porosity, and if those pore spaces are connected enough, then we have the right conditions for an aquifer. So there are two main types of aquifers: confined aquifers and unconfined aquifers. An unconfined aquifer lies right beneath the ground surface, with its upper layer open to the atmosphere through the soil. The top of this aquifer is the water table, which rises and falls in response to rainfall or drought. Because it is directly connected to the surface, an unconfined aquifer is easily recharged by rainfall and surface water. It can be thought of as a sponge sitting on the ground. Water can just soak in and out freely. A confined aquifer, on the other hand, is sandwiched between impermeable layers such as clay and shale. Its upper boundary is sealed off, so the water inside is under pressure. Unlike an unconfined aquifer, the water table here is not exposed to the surface. Confined aquifers are only recharged where the water-bearing layers are exposed at the surface, often far from where the water is accessed through the well. They are best compared to a sealed pressurized bottle. Once opened by drilling a well, the water can just shoot upward. So I couldn't do an episode on water resources and not talk about Darcy's law. To understand water movement in aquifers, hydrogeologists, they use Darcy's law. In 1856, Henry Darcy, or should I call him Henri Darcy, because he was a French engineer, was tasked with improving the water supply system for the city of Dijon. While experimenting with sand filters, he observed how water moved through porous media. From his experiments, he derived a relationship describing the flow of water through sand columns, and this became Darcy's law. He probably didn't imagine his sand experiment would become the foundation of hydrogeology, though. But anyway, Darcy's law tells us that groundwater flow depends on the permeability of the material, called the hydraulic conductivity, the area available, and the slope of the water table, or the hydraulic gradient. It is written as Q equal K times A times delta H over L, where Q is the discharge, or the volume of water per time, usually in meters cubed per second. K is the hydraulic conductivity, how easily the medium transmit water. A is the cross-sectional area in meters square usually, and delta H is the difference in hydraulic head. Just think of it as the change in height. And L is the length of the flow path. This is Darcy's law in its most basic form. It can get a lot more complicated. The more advanced in hydrogeology you get, the more challenging it becomes. There is some very high level math here, which I still struggle with to this day. But this is the foundation that underpins our understanding of groundwater movement. So I have a scenario for you. Based on the geology of the area, we know that the rock exhibits high porosity and permeability. Our investigations revealed significant quantities of groundwater, and calculations using Darcy's law confirmed that substantial amounts of water can be transmitted through the geological medium. And from this, we determined that the aquifer is economically feasible. So, what comes next? Well, extraction, But how do we actually extract water from the ground? This is where an extraction well comes into play, a method widely used in aquifers all around the world. With growing populations and expanding cities, the demand for fresh water continues to rise, driving the development of groundwater resources. However, if aquifers are not managed carefully, overexploitation, particularly in the face of climate change, can lead to serious problems. Coastal aquifers may suffer from saltwater intrusion, and this is a case in many parts of the world, and in extreme cases, we have land subsidence occurring. And this highlights the growing importance of effective groundwater resource management to ensure sustainable use of this critical resource. So it really goes without saying why this matters, right? This is water, and as they say, water is life, right? We study aquifers to understand how they behave and better manage our water resources. Understanding groundwater is critical as we move on into our future. So it's really that simple. I don't think it needs as much explaining as most other things that we've covered on in this series. So that concludes our exploration of water resources, very critical to human survival. We learned that a small portion of the water on Earth is fresh water available for human consumption. We looked at porosity, permeability, the types of aquifers, Darcy's law, and groundwater extraction. Join me next time when I explore energy resources, another set of resources critical for life as we know it on Earth. So until then, take care and thank you for watching.